this second half of the third lesson, 7.3, when we're still working with special products, but a different example, is so much easier. You guys are going to love it. Even if perfect square trinomials on the previous lesson didn't quite click just yet, and maybe you're practicing it a little bit more, I think you're going to find that this one is super easy, super fun. And in fact, I'm going to say something really important about this lesson, and that is that although this one is awesome, you're going to see how easy it is. You can kind of already see it just in these examples, and you're going to see it at play. It is also the most important one out of these special kind of special products, because I keep sort of foreshadowing a little bit, if you know what that means, kind of hinting at what is to come. And although both of these are shortcuts right now, the perfect square trinomials from the previous lesson and this difference of perfect squares from today, right now they're shortcuts that are just going to save you that box method or that FOIL time. And if you don't remember them, it's really not the end of the world. A little bit later, we are going to be going in the opposite direction, right? So in a few weeks, instead of trying to multiply these guys together and get this result, we're going to be starting with the result and trying to figure out what binomials were multiplied, okay? Or what factors were multiplied to give us that. And when we go in that direction, then, as I said on the previous lesson, perfect squares, it's going to save you a lot of time. Instead of just a little bit of time, it's going to save you a lot of time. However, today's lesson, and hear me out if you hear nothing else, for today's lesson, you have to know this pattern, or you won't be able to get back to this original. So knowing this pattern is the only way that later on you're going to be able to go from something that looks like x squared minus 9 and be able to say, oh, that really was the product of x plus 3 times x minus 3, okay? So although this one is a lot easier, it is also a lot more non-negotiable, okay? It's easier, but it's also a lot more critical that you understand it and know it, especially, like I said, in a few weeks. Right now, it's a shortcut. In a few weeks, it's going to be absolutely imperative that you know this pattern so you can go in reverse, okay? On the other ones, it'll save you some time, but it's not the end of the world. Here, it is just, if you don't know the pattern, you're just going to get the problem wrong, and that's no good, right? So, as you can see, looks like a really simple scenario, but of course, you know my game. I really like to explain to you why things are what they are, okay? So the difference between perfect squares basically states that if you have two binomials that are almost exactly the same, but not quite, okay, maybe they have the same two terms like this, but the signs are different. That's what's different. Well, that's what's like special about these. So I always remember, difference of perfect squares means that they're different signs. One's a sum, one's a difference, okay? When that happens, then the result, whether you go the long route with a FOIL or the multiplying, or you remember this shortcut, the result always ends up being the square of the first term minus, it is always a minus, the square of the second term, okay? And again, that's why we call it a difference of perfect squares. I like to think of it as a difference because I know my signs are different, and it's also a difference because difference means subtraction, and it is a difference of perfect squares. That is literally the name of it, okay? But why does that happen? Well, check it out. Let's actually just use this example again, and let's FOIL it to see what happens if we just did this the good old-fashioned way. I would do the product of my first two terms, x times x, that's x to the second power. Then my outer terms, in this case, x times a negative 3. So that's negative 3x. And then my inner terms, which are a positive 3 times x, which is a positive 3x. And then in the last one, it's going to be a positive 3 times a negative 3. Well, a positive times a negative always gives us a negative, and 3 times 3 is 9. So here's the main difference between what we did on the previous lesson with perfect squares. When they were the same binomial, right, when we square, we got two identical terms, so it doubled. That was on the last lesson. In this one, since they are almost the same but the signs are different, instead of these two middle terms doubling up and us multiplying by 2 like we did before, instead of these doubling, you can see already here that instead they cancel. They end up being exact opposites. Instead of exact sames, they end up being exact opposites. And so when I combine here, when I go to combine these, they actually just zero each other out. And I'm left with just that perfect square at the very beginning. And then the negative, now you know why this is always a minus, because you always end up with a negative since you're multiplying different signs here, right? You always, and then the negative of that perfect square. And that's why the answer is what it is. So that middle term that typically is in the center, creating the trinomial, cancels itself out. Instead of doubling up like it did on the previous lesson, it cancels and disappears. And we really just end up with the first term squared, and then a subtraction or the difference, and a perfect square over here. Okay, so that's really nice. And once you catch on and you realize that that's going to happen every time you have the product of binomials that have the same two terms but different signs, one's a sum, one's a difference, this is always going to happen. And all of a sudden, this got really easy, right? Because as soon as you can identify that it's that special type of product, I can say, oh, you know what? These are same binomial but opposite signs. So my result is going to be this first term squared. So that's an x squared. And then the different signs are going to produce a negative in the middle there. And then 3 times 3 is 9. So that's really the same one we did here. I just realized that. Okay, let's try the next one though, because it is that easy. So instead, and again, if you kind of forgot that, you could FOIL it out. You're still going to get the right answer, but man, this saves you some time. If you see you have the exact same two terms, one's a sum, one's a difference, they just have opposite signs, then our result is just going to be the square of the first term, and then opposite signs give me a negative, and then the square of the second term. So the square of 5 is 25, and that's going to be our result. If you're not sure, use your box method or FOIL or so forth and test it, and you're going to see that's exactly what you get. Okay, let's try number 3. Gets pretty easy after this. You can start to see the pattern there. If we multiply two binomials that are almost identical but with different signs, we know the drill now. We'll just square the first term. So if I have 5a and I square 5a, meaning 5a times 5a, I'll get 25a to the second power. Put my subtraction. Two signs are different, and 1 times 1 is still 1. So there's our difference there. Okay, this guy might look intimidating, guys, but it's no different. Okay, and if it helps, maybe just write out that square, right? So maybe in the first part you might want to put this intermediate step that says, okay, I understand it's going to be that very first thing to the second power, and that second term, the ones, to the second power, and then maybe after that you square it. So it's going to be all of this first term squared. Well, when I square that, I'm going to make sure I do 1/4 times 1/4, so that's 1/16, and b times b, which is b to the second power, and then we'll have our minus, and then 1 times 1 is 1. So that would be our product. So again, just square the first term, and then put a little subtraction in the middle, and then square the last term. Okay, so again, here it's going to be negative 3j being squared minus that 2k being squared. And so if we square that, we end up with 9j to the second. And then always have subtraction in the middle, and then 4k to the second. Okay. That looks great. Okay, on this one, be a little careful. The ones that have the opposite sign are in front here, and so it's still going to be a difference, but we need to be careful with our sign here, right? So if the same thing would happen, but it would happen in a slightly different scenario. So the ones that have the opposite signs here are the 6a. So when I square those are the ones that are going to stay negative here. Okay, and if you don't like that, you could just swap these around if you wanted to. But we're still going to get the square of this first term and the square of the last term, but the one that's going to have the negative is the one that has the different signs, which for this kind of odd example, it doesn't happen a lot. It's actually the front one. And then these are both positive, so it's going to stay positive, and then we're going to square. 1/2 times 1/2 is 1/4, and b times b is b to the second. Okay? Okay. That's the pattern. It is really that simple and that easy. So if you look here, we can also work this. And again, this is not quite as relevant. I think it's kind of neat to see that it works with numbers, although I know you have a calculator and most often you'll reach for it. I want to show you how it could still work with numbers here. So the idea here, like we did on the previous lesson, is we could rewrite these kind of like a difference a difference of perfect squares to make the math easier. So I don't know what 18 times 22 is, and I would have to go and compute it all out. But one option I could do is write 18 as the difference of 20 and 2, and 22 as the sum. So I'm able to write, for these two, I'm able to write them in terms of the same numbers, once a difference, once a sum. And so even though I didn't know this off the top of my head, I definitely know these, right? So 18 is 20 minus 2, 22 is 20 plus 2. I now have a difference of two things that are the same here. So it's going to be the square of the first term minus the square of that second term. Well, that's just 400 minus 4. So 396 must be the product of those. Okay, we don't necessarily have to do a whole lot of those, but just so you could see that you could do it with numbers as well. So go ahead and flip that over. Let's try a couple of word problems now that we know what that pattern looks like. So let's check out number 9. On number 9, it says, this week, Kiara worked X plus 4 hours. She is paid X minus 4 per hour. We want to write a polynomial for the amount that Kiara earned this week. So we know that typically the total that we get paid is typically, our salary times however many hours we work. Like if I get $9 an hour and I work for 4 hours, I know I get $36. Or if I get $10 an hour and I work 7 hours, I'd multiply those and say, oh, I'm going to get 70 hours. It's a multiplicative type of problem. Okay, so in this case, my salary is X minus 4, or my hourly pay, I should say, and I worked X plus 4 hours. So I know if I multiply those, it'll tell me how much I've earned. So the first part of this is write a polynomial. So I'm not going to worry about this yet. I haven't read that far, and I need to make sure I do this in order. So the first thing is write a polynomial for how much they earn. This is the setup, but you need to go ahead and work it out. But before you work it out, if you catch, oh, but these are actually the same, except one is a sum and a difference, then I know very quickly that it's just going to be the square of the first term minus the square of the second term. And so that is the first part of this problem. This is going to be how much the total that she earns in a week. It's the product of how much she gets paid per hour and how many hours she worked. But that product is just the difference of squares, or a difference of perfect squares. So now that I have my polynomial, that's part 1 here, okay? So I can check that off and say, okay, I've done that. Then they want me to calculate this pay if X is 12. So now I can find out, oh, okay, well, if X is 12, I'm going to insert a 12 right here for X. I can work out how much Kiara made. So this is 144, that's a perfect square, minus 16. Looks like that comes out to 100. I believe that's $128 that she'll get paid this week. X is 12, but let's check to be sure. So on my calculator, if I do 12 squared minus 16, it is 128. There you go. So she gets paid $128. All right, let's try number 10. It says a museum set aside part of a large gallery for a very special exhibit. So here's our exhibit. This is the whole gallery, I guess, and this is our exhibit right in here. We want to write a polynomial for the area of the gallery that is not part of the exhibit. So we want to end up with a polynomial that represents this space out here. Okay, then we'll calculate it for when X is 60, but we're not there yet. Let's first focus on the polynomial. Write a polynomial for the area of the gallery that is not part of the exhibit. So we already did one of this a couple days ago. When we have kind of an irregular shape, the easiest plan is to find the area of the large, easier shape, find the area of the part you want to, omit, and subtract those, right? So we're going to do, essentially, we're going to do area of the gallery minus the exhibit area. Okay, so the gallery is a rectangle that has dimensions x minus 8 by x plus 8. And right away I recognize that this is a difference of squares. They are the same except my signs are different, so I can use my shortcut. The area of the gallery is just going to be the square of the first term minus the square of that 8, which is the second term. So that right there represents the area of everything, the whole gallery, or the whole gallery floor. Okay, now I need to calculate the area of this exhibit, which has dimensions of 0.5x plus 1 by another 0.5x plus 1. This is a square. They're both identical, so I can use my perfect square trinomial pattern for this guy. Okay, so let's practice that. This is good to practice. We already figured out the gallery area. And now let's use our pattern from the previous lesson. So the pattern for perfect squares, when you're multiplying it by itself, it's similar, but we're going to have that middle term. Instead of it disappearing, it's doubling. So first it's going to be the square of this first term. And so if you need your calculator, 0.5 squared is 0.25. So 0.25, and then x times x is x squared. So there's my perfect square at the beginning. In the center, it's going to be the product of these times 2. So 1 times 0.5x is still 0.5x, but I'm going to have 2 of those. So I know that 0.5 and 0.5 is just 1x. So in other words, if I have 0.5 times 2, I get 1x. Okay? So that's my middle term. That's the pattern. And then the last term is just the square of that last term. So 1 squared is 1. So this is the space that the exhibit is taking up. This is my entire galleria. This is what the exhibit is taking up. I want to find the difference. That's our goal. Okay, now be careful with these. Again, when we're subtracting, you have to make sure you distribute that negative and essentially switch all your signs. Okay, so we're going to have this x squared minus 64. We're going to subtract 0.25x squared. We're going to subtract the x, and we're going to subtract the 1. All those signs that were originally 3 positives now become 3 negatives, or in other words, we're subtracting each of those terms. Okay, now let's combine what we can. I have a couple of x squareds here. So this, remember, this has a 1 if I don't see anything in front. So 1 minus 0.25 is 0.75. So that kind of takes care of these guys. I have an x term here that doesn't combine with anything else, so that stays. If you want to cross it out because you're done with it, sure. And then I have that negative 64 and now a negative 1. That's going to be negative 65. This right here, guys, represents the area of that shaded part that I shaded in here, which is basically the part that is not in the exhibit. That's our area. Okay, so that's what they wanted for part 1. Okay, so I can say, okay, got it. I already did that. I wrote the polynomial for the area that is not part of the exhibit. Then they want us to calculate this area when x is 60. So now all I have to do is insert a 60 here. And say, okay, if we make a 60 here, and a 60 here. Anytime I see an X, I'm going to insert a 60. Notice I am definitely going to hug those in parentheses. That makes a really good big difference. It's going to guarantee me that everything I do is correct. Then I can just throw this in the calculator. 0.75, I insert my 60 and I square it. And then minus, I insert my 60. And then minus that 65. Calculate it out. Well, it looks like that area, when X is 60, that area is 2,575. And I wonder, they didn't give us units. So there you go. So maybe just say square units. And there's our area. Okay. All right, take a look at number 11. Try that one out, and we can go over any questions in class.